Gotta get moving. Gotta get moving. Gotta get moving. Yeah, we're gonna talk about the forces of motion today. You heard of that scientist who had an apple drop on his head, Isaac Newton? So we're gonna learn about Newton's three laws, and they all have to do with motion. So our first learning target is I can give an example of Newton's first law describing inertia. Our first term is Newton's first law. Say it with me. Newton's first law. Newton's first law says an object at rest remains at rest, and an object in motion remains in motion at a constant speed and in a straight line unless acted on by an unbalanced force. See my pen there? It's just resting there, and it's happy unless I move it. It will remain there unless something moves the pen. It will remain there unless an unbalanced force acts on it. Remember we just talked about balanced and unbalanced net forces? Yep, now we're going to apply them. Newton's first law is also sometimes known as the law of inertia. Here's our next term, inertia. Say it with me, inertia. Inertia is the tendency of all objects to resist changes in motion. This is why it's so hard when you're oh, I think I'm going to stand up, and you're it's so hard to get up. It's because you have to actually work. You have to apply a force in order to move yourself. So inertia is the tendency of all objects to resist changes in motion. So it takes a force. Friction. Say it with me. Friction. Friction is a force that opposes the motion of an object. So if I'm going to move something, I have to move it against other objects, right? Like air or the carpet or something for example, my pen is rubbing on the paper, right? That inertia says this wants to be still, but if I push it, it will stop. And it stops because it's kind of dragging on the paper. And that's friction. That's the interaction between the paper and the pen. So today on notebook page 60, you're going to draw an example of a situation involving inertia and explain how it demonstrates Newton's first law. You're going to watch a video, and I'll have a lesson shortly after this, so you should be able to get a good idea to do it. All right, next notebook page today. Yes, there's another law. And we're going to look at all of them because we are so smart. There are actually three laws, so three notebook pages. Our next learning target is I can use Newton's second law to demonstrate how the acceleration of an object depends on the mass of the object and the amount of force applied. Wow, that's a lot. So here's what Newton's second law of motion says. It says the acceleration of an object is dependent on the net force acting on the object and the mass of the object. It means that force is equal to the mass times the acceleration. Oh man, Mrs. Tomlinson, that was so much. Okay, so let's take this Post-it as an example. This packet of Post-its. It's going to take me more force to push this packet than it will to push this packet because this one has more mass, right? So it's going to take me more force to push more mass. That's all it says. Then it says, if you use the same force, so let's say use the same force on both of them, one of them is going to go farther than the other, and the one with the less mass will go farther with the same amount of force, right? So then we have to use something called acceleration. Acceleration. Say it with me. Acceleration. Now, you and I probably think of acceleration meaning speed up, use the accelerator. Well, yes, acceleration is the rate at which velocity changes, but it could be speeding up, slowing down, going around a corner, changing directions, okay? Any of those things is acceleration. On notebook page 61 today, you're going to draw an example of a situation involving acceleration, and you're going to explain how it demonstrates Newton's second law. All right, last notebook page, last two laws. I know you thought there were only three, but there's actually four. So there's only three Newton's laws of motion, but there is one law of conservation of momentum. So Newton's third law. I could explain what happens when objects collide in terms of Newton's third law. We actually like when objects collide, like humans. We actually like it when they crash. And then we're like, oh, look at that. Well, Newton's third law kind of explains it. It says, if one object exerts a force on another object, then the second object exerts a force of equal strength in the opposite direction on the first object. So if I am holding my pen up, my pen is also pushing my hand down with an equal and opposite force. With an equal and opposite force. So that's when momentum comes in. We have to look at this. Newton's third law is sometimes called the law of momentum, right? A momentum is a characteristic of a moving object that is related to the mass and velocity of the object. For example, right now, if I threw this pen at you, you wouldn't really think much of it. But if I took this cup and I threw it at you, you'd probably get out of the way. Right? I mean, either way you duck because it's danger, but which one would you be more afraid of? The small mass or the large mass? Hopefully you would be more afraid of the large mass. So that's what momentum is. Momentum just says the bigger something is when it's moving, the more kind of force it carries with it, okay? Has a bigger mass and kind of has a lot of velocity, so speed and direction. Okay, to carry with it depending on the mass. So if you have a greater mass, you have a greater velocity. Okay? Then there's something called the law of conservation of momentum. It is the total momentum of any group of objects, and it remains the same unless outside forces act on the object. So what momentum, the conservation of momentum means, is if one object hits another, it will transfer its energy to it. Kind of like, have you ever played pool? Right, where one ball cracks into the other and moves it? Well, let's look at it with Post-its. If I'm going to take one Post-it and smash it into the other, this one's going to stop and that one's going to move. Right? The momentum transferred from here to here. Okay? That's how it works. That's the law of conservation of momentum. Neither one of them got more energy, but one was moving at a steady pace and it ran into the other and stopped and transferred its energy to the other. Okay? On the bottom of page 62, you're going to draw an example of a situation involving momentum and a situation that involves two objects colliding with action and reaction forces. I'm going to cover that in the video right here. All right, remember you can always come back to this video and you can press pause at any time so that you can come back and be like, what was that thing that Mrs. Tomlinson was talking about? Because I know you're not paying attention anymore. Wake up, wake up, wake up, wake up, hello. Okay, here we go. This is the Newton sitting underneath his apple tree, and what he found out is that, gravity pulls things down, right? But as we know from our last lesson, we know that these apples hanging from this tree right now have a net force of 0. They are not moving. But once one of them starts moving, like let's say the apple starts to fall, that means that a force has acted on it. What force do you think that is? If you said it was gravity, you are correct. All right, so let's look at Law 1. Law 1 talks about inertia. And today what you're going to do is you are going to do an activity with a coin. You'll put it on an index card in a cup, and you're going to pull the index card out super fast, and the coin will fall into the cup. So the coin will sit there as long as it is sitting there, right? It's just resting. It's not moving at all. But once that card is moved, then that coin is going to go down because gravity is the unbalanced force that's going to act on the coin, and it's going to fall into the cup. Okay? So let's look at this in a different way. Let's say we have all of these gumballs in a little, cart, and the cart continues down the slope. It's going to keep going, keep going, keep going, keep going, keep going. But then if you put a barrier in front of it, an unbalanced force, right, that's going to press against it, and it's going to press against that, the gumballs at the top that are not stopped will continue moving, right? Because they like to keep moving in a straight direction forward until something stops them, okay? All right, so inertia also involves different objects, right? So really, Law 1 says an object at rest will remain at rest. So the soccer ball is just going to sit here until the foot kicks it, which is an unbalanced force, right? It's going to unbalance it, and then the soccer ball will become in motion. And it will go on and on and on forever Wait a minute. We have to think about that. Have you ever kicked a ball? Did it ever stop? You bet it did, because there are two forces acting on it. The first force acting on it would be gravity, right? That's going to pull it down to the ground. And the second force acting on it is going to be friction. So when that soccer ball gets down into the grass, friction is going to slow that soccer ball down. So, but this soccer ball, once it gets kicked, will remain in this motion until gravity and friction act on it, okay? And it will keep on going until it gets stopped by an unbalanced force. In this case, it's the soccer net, right? It's pushing on the soccer net's pushing on it, and it has to slow down and stop. All right, Newton's second law. It basically says that if the same force, sorry, I know you guys can't see all of this. Let me see if I can't do better. There we go. Okay, so Newton's second law says if the same force is applied to an object with greater mass, the object accelerates at a slower rate because mass adds inertia. Let's pretend these are shopping carts, okay? Have you ever pushed a shopping cart? I'm sure you have, or you've pushed someone or something. And so you know that if you use the same amount of force for whatever it is, if you use the same amount of force and something has less mass, it's smaller, the speed is pretty fast. If you use the same amount of force and you add mass, like it's a bigger thing, it won't move or accelerate as fast, right? So the more massive something is, the more force it takes to make it accelerate. So here we have a less mass, more mass, right? Same amount of force. If you have less mass, you get more acceleration. If you have more mass, you get less acceleration, okay? All right, here's another idea of that if you've ever pulled somebody maybe on a sled lately, right, or in a wagon. So basically, to get the wagon to accelerate, it's just going to sit there until you move it. So you have to pull it, right? If the mass in the wagon is more, so like it's so much harder to pull 4 people than it is to pull 1 person, if the mass of the wagon increases, a greater pull is necessary to move the wagon. We know this firsthand. I'm sure you guys have pushed or pulled each other around. Okay, our third law talks about momentum. And here's a really great example of it. A moving boulder has more momentum than a stone rolling at the same speed. So if we had a little stone about this big and it's rolling, which one are you going to run away from? Not necessarily this one. I mean, who cares? It's just a little tiny stone. Probably won't do much damage. But you're definitely going to run away from this one, okay? So this one has more mass, so it has more momentum, okay? So a faster boulder has more momentum than a slower boulder also, right? So if it's going faster, it has more momentum. If it's going slower, it has less momentum. Think about like when you have last run into a wall. Has anybody ever run into a wall or a window? Okay, when you hit that thing, if you were going slow, it was really no big deal. But if you were going fast, it was a big deal, like caused a lot of damage, right? Because you had more momentum. So a boulder at rest has no momentum. So if it's just sitting there, something has no momentum. Now let's look at action and reaction forces, because the third law also says that for every force, there's an equal and opposite force applied, right? So let's talk about a gun. So the action of a gun is accelerating the force of the bullet. It's making the bullet go. But the reaction force is that the gun recoils and comes back, okay? So like if you're walking on the floor, if you do this right now, you could do this. You could put your foot down and you could stand up. So the action force is the foot pushing down, right? And the reaction force is the floor pushing back up, okay? So just like I was holding my pen, the pen is pushing down and my hand is pushing up, right? To hold it, to make it float there. All right, so here's one. The action force here is the boy's feet exert force on the boat. And what's going to happen? The boat is going to exert force on the feet. It's an equal and opposite action and reaction, okay? Equal and opposite force. These are actually really kind of fun. Enjoy the videos. You have nothing to submit today, but you do need to complete all 3 notebook pages. All right, I hope you learned something, and I hope you're getting out there, moving and exploring the 3 laws of motion. Motion, motion, motion.